Okay, welcome to lecture 15. Today we're going to go on looking at the limit cycles, and in particular the Poncarbon theorem, which tells us when a limit cycle occurs. And so what we did last time is we had this theorem that I said results basically, it's only valid in 2 dimensions. It results from the topology of 2 dimensions, namely that you have a unique solution that implies that your trajectories don't cross, and so that if you can find a region R where that doesn't contain fixed points that the trajectory can run to, so in other words, you've cut out all the fixed points, and you can prove that if a trajectory in R at a time t0 remains in R for all time after that, then you have this theorem that either your trajectory is a limit cycle or it is going to spiral to a limit cycle, and that thing results simply from the fact that it's got nowhere else to go and it can't cross itself, right? So you basically have this idea that the limit cycle is here. Now the hard part in this theorem is actually proving or finding this region R that you can use to apply the theorem and then proving the trajectory stays in it. So the tricky part to prove is basically there exists a trapped trajectory in R. And often what we do is we don't prove it with a given region R, we actually choose our region R so that this remains true. And so I'm going to do a number of examples today of how you go about choosing it. Okay, so the usual application of the Poncarbon theorem is find a curve, okay, for example an annulus, right? It's an oftenly chosen curve. I'll give you a whole list of other examples we'll see, but just the easiest example. So suppose you have, say, 2 circles or an ellipse and a circle, which is what I actually do there, and make sure that the flow on the boundary is inward for every single vector on the boundary. So suppose you have the flow over here on the outer boundary, it's inward. In other words, you're going to have, at every single point on the boundary, the arrow is always going to point into the domain. So you're going to have a flow like that, okay? And similarly over here, if it's a donut-like thing, every year on this boundary, you're going to have that the flow points inwards, and you're going to have that there are no fixed points in this pink region. Okay, so you've cut out any fixed points, and you can work out the vectors. So that's going to be the way we construct the boundaries to be able to apply this theorem. We want special curves where we know what the arrows are doing. So another class of special curves that is also quite useful is null lines, right? Because you know if you don't have fixed points, it always points the one way across the null line. It's easy to calculate, and we use that quite a lot as well. Okay, so then if you have set up that thing where you've got your 2 boundaries where the arrows are always pointing inward for every single point on the boundary, and that's important. You can't have some points where the arrows point out because your trajectory can escape there, so then you don't have a solid proof. Okay, then every trajectory in R is trapped, and therefore there exists at least one limit cycle or trajectory in R. Okay, we haven't shown that it's unique because in fact you can have a limit cycle over here and you can have a limit cycle over there, and you'll still be able to satisfy these conditions. But you've at least shown that there exists just one, at least one. Okay. And so once you have that, you can apply the Poncarbon theorem, and you've proven that the limit cycle is there. You don't know what it looks like, but you know it lies between those 2 boundaries. And this sort of gives you the idea of what you have to do whenever you want to apply this theorem. The hard part, as I said, is finding this thing so that you can get a boundary where all the arrows point into it. That's tricky. And so we're going to look at a number of examples of that. So the first thing we're going to do is consider examples, and in its example from our first, sort of a generalization from our first example, we're going to give it in polar coordinates. In other words, we have r dot equals to r times 1 minus r squared, and this thing we had in the past, right? It was our first example of a limit cycle. We had this, and now we're adding something that is not spherically symmetric. Because remember, we could prove that this thing, if you look at just this part, it has a limit cycle of 1. But we're now adding something that makes it obscure. If you were to actually have written this thing in the original Cartesian coordinates, it would have been even weirder. You would have been less obvious that there was a limit cycle. And your theta component is just increasing with 1. Okay. So, and mu's a constant, and when mu equals to 0, we are back to the case where we've already looked at, where we have a limit cycle at r equals to 1. If mu is non-zero, we now want to define a trapping region, and we want to apply the Poncarbon-Bendixson theorem. And so what we're going to do is we want to show that for all small mu not equals to 0, the limit cycle stays on. And this idea of a structure being there and then persisting if you change the parameters becomes a very important theme in dynamical systems later on. It's called structural stability. In other words, the structures you have are robust and are there. And eventually when people start dealing with chaos, this becomes an important thing too, because chaos, you cannot describe deterministic, you can describe, it's deterministic chaos. You cannot find the answer in closed form, but you can still say a lot about what it behaves like. And you can actually show that those structures inside of it is robust. Okay, so it's a very cute thing when you go past 2 dimensions and we start looking at chaos. There are structures in chaos that even though you can't get the exact answer out, you can say a lot about the structures and you can say a lot about how the chaos forms, and you can show that those are robust. So here we're trying to sort of get a first introductory example as well. We have an equation, we change it slightly, and we want to say the structure in the equation persists for small mu. Okay, in other words, there's a closed orbit near r equals to 1, although it's no longer a circle. Okay, so we're going to use it by applying the Poncarbon-Bendixson theorem, and to do that we need a trapping region. Okay, so the first thing we want to do is we want to have, and because this thing is, mu is small, and this thing is almost spherical, it's a good guess to have a trapping region. Often what your dynamical system looks like allows you to guess what the trapping region is. So in this case, it's a good guess that that's a circle, because you know the limit cycle that you're changing from originally when mu is 0 is a circle. Okay, so we want an R max so that R decreases, R dot is less than 0. In other words, it points inwards along the whole of the R max. Okay, so we want R max so that all the arrows in R max does that way. So if you think about it now, theta dot is always increasing. So they're always going to point basically in a counterclockwise direction. And you want R dot, you want to be negative. In other words, it's always going to be pointing inwards towards the center. So that's the one thing, but we know the system has a fixed point at r equals to 0, right? If r is equals to 0, r dot is equals to 0, theta dot is not. But remember, when we're in Cartesian coordinates, it is r times cos theta and r times sine theta, so it is a genuine fixed point. Okay, so at 0, we know we have to cut that out, so we want a minimum r so that r dot is greater than 0. Okay, so we're going to cut out our fixed point. We're going to have this minimum r, and we want r dot here to point across these things. In other words, we basically want to set up the following structure. And the question now is, can we find a maximum r and a minimum r so that that is true? Okay, and so you can see the strategy here is we've guessed that the domain is a donut, and we're going to now try and adjust the boundaries of the donut so that we have a region in which the flow is inward totally into the region. Okay, so firstly, you have to check all the parts of the theorem. The function is continuously differentiable on that region. There are no fixed points because we've cut out the center. And by construction, if we can find r min and r max, the trajectory in the region is going to stay in the region. So we've satisfied everything if we can find r min and r max. Okay. And the reason for showing robustly that there's no fixed points in r is simply to say theta, for non-zero r, theta does increasing though, so the thing is always going around like that. Okay, so now we want r dot greater than 0. Okay, in other words, we want to look at the blue region, and we know r dot is greater than 0 if this thing is greater than 0. Okay? And we want an expression for r, because we've chosen r to be a constant. And we know this thing is greater than 0 if it is true for every single theta. Okay? And we know that theta is greater than equals to -1. So this thing is greater than 0, provided it is greater than 0 for the smallest theta. In other words, provided this is true. Okay? So here we now have an inequality just for r and your mu, and you can say that if this is greater than 0, it guarantees that r dot is greater than 0. And so for r squared less than 1 minus mu, we have a valid inner circle. Okay, so we're going to choose our r min, any number less than 1 minus mu, the square root of both of those, of the whole thing. Okay, so in other words, the maximum minimum value it can have is the equality. If r min is anywhere between that and 0, but bigger than 0, then it's a valid r min. And typically we want to choose the smallest region. In other words, we want to choose the biggest r min possible so that this thing is still true. So we're going to choose r min basically equals to that minus epsilon. Okay, and the reason for that is the more finely you can confine your limit cycle by putting the bounded region, making the region as small as possible, the more closely you know what your differential equation is going to do. So you always try and get the smallest possible trapping region. Okay, so that'll work, and it'll work, once again, put in the conditions, provided mu is less than 1 for the thing to be defined. Once the damping gets too big, you can no longer use this method, okay, because you can't find a minimum r min. Okay, r dot is less than 0. In other words, we're now going for the r max value. If we do the same argument, okay, if this thing is true for all theta, and here we have to choose theta is basically plus 1, and we have that 1 minus r squared plus mu must be less than 0. So it's the same argument, just where the inequality is reversed. And so we have that r max is greater than the square root of 1 plus mu. Okay, so we now have gotten our minimum and our maximum radius that bounds the region. We've ensured by their construction that flow obeys us. In other words, it's inward at r max and outward into the region for r min, and we're basically done. Okay, we can apply our Poincare-Bendixson theorem, and we've proven the moment we have r min and r max that we have a limit cycle between these two boundaries. And you can see what's also nice is as mu goes to 0, you know exactly where your limit cycle is. You have that your limit cycle is between these two boundaries. When mu goes to 0, you have that the limit cycle is at 1. So that's just a check. You must check that your original limit cycle that you know is still satisfied in the boundary. And so what typically happens is that the limit cycle occurs in here, but it is no longer a circle. It has an angular component. So it basically looks very similar to the thing I drew, just a little bit rotated on the previous slide. Okay, so that's one example of how we guess the trapping region. It's not the only way. So you can see the only thing we require is a region where the flow is inward on all the boundaries. And so what we can do is, one, we can use polar coordinates, and this is just generally like a checklist I run through if I'm starting a new problem. I can use polar coordinates, for example, circles that I've done in this example. I can look at a rectangular region. So typically you choose regions that are easy to calculate on. So a rectangular region is just fixed coordinates. If you can show that it goes inwards along all the on all the lines, then you're fine. Okay, so it's easy to evaluate your differential equation on a rectangular region. You can also make a whole bunch of straight line boxes, in other words, which is what we'll do in the next example. It's sometimes sometimes constant coordinate lines, you don't have arrows that just point in one direction or just cross it in one way. And then you can change the angle of the lines and make a collection of them to actually get a region where you always have arrows pointing inward. It's just more work. In fact, another thing that's also very useful to use is you use the null clines of a problem. In fact, you plot them first so you can get a feel of what's going on. and then you start guessing or sort of using parts of them in your solution. In other words, x dot equals to 0 or y dot equals to 0. And finally, you can use the trick that we used when we looked at dissipation in the a pendulum and the double well. You can use the potential functions. Okay, you can have this idea of a function that's different from the differential equation, and if you can show for a contour of that function, E dot, say, is always decreasing, then it basically is flowing inward. And so in some sense, that's actually a generalization of the circle idea, that you just have these contours. If you can find a contour where everything is going in, then you're also done. Okay, so let's just look at a more complicated example. And this example comes from glycolysis. So glycolysis is basically how any human body or plant or whatever changes sugar into energy. Okay, and what we have is it's basically how they get the energy comes stored in sugar. It gets broken down during the process of glycolysis, and it is the most efficient way of storing energy that we've come across. I mean, the human body is amazingly efficient. We all talk about these sort of energy conservation and energy machines, and you forget to think of completely what you can do, the computational power you have, how much you can move, what you can respond to. It's totally amazing. Anyway, so this is a model of people that try to understand glycolysis. I don't know what the origin was. I mean, it's been very much used in sport, right? You have the ideas of, you have anaerobic and aerobic respiration. This is aerobic respiration. And people wanted to understand that to compete in a better way, to know how much recovery times you have, what you should do to actually have an optimal performance. So there's a lot of reason to try and understand the cycle. So our simplified model is simply also has an oscillatory process. So they've seen this thing in yeast, and this is where it was studied a lot. Sort of if you want to brew beer, you have to understand the cycle. You have to understand the time scales, how long you have to keep the beer in a certain temperature for it to ferment optimally. Same thing if you want to make wine. So there's a lot of reason to understand this. And people have noticed that it's an oscillatory process. In other words, sugar comes in, it gets used, the blood takes away the waste products, more sugar comes in. So there's a time period to how the sugar is burnt. There's actually a time period in any engine, right? So if you have a car engine, the cycle, the way the pistons go in, it also is an oscillatory process. Okay, so the model comes from Selkoff in 1968, and the model he proposed was basically this. It's a linear model in X and Y, and then it has this cubic term that's the same. Okay, so this is the simplest model that would then suddenly start doing glycolysis in certain regions. I don't know exactly how he derived it. You'll have to go back to his original paper. But what I'm going to do is basically analyze it mathematically now. Okay, so A and B are assumed to be greater than 0. They are kinetic parameters, basically how efficient your yeast is, how rapidly it breaks it down, and so it's dependent on the system. And they wanted to know what region you have to choose these parameters to actually get a cycle that actually is going to convert the sugar, because it doesn't always happen. Okay, so this is the basically the thing that's breaking it down, and this is the amount of sugar, and they saw that these things oscillate, and we're now simply going to look at how. Okay, so let's analyze the model. We do exactly what we've been doing in the past, fixed points. Okay, and to get the fixed points, you basically have to solve these two equations equals to 0. And when I solve these equations, it's slightly more complicated, right? It's a cubic. The first thing I do is see how I can simplify the equations as much as possible. And one way I always want to simplify things is I want to get rid of the most complicated term. And here it's fortunate in that this x squared y and this x squared minus x squared y appears in both. So I'm going to subtract the two equations before I do, or add them before I do everything else, to get rid of this, to get rid of the cubic term. And what I'm left with is minus x plus b, which I can solve. Okay, so basically for a fixed point, I now have x equals to b. I substitute this back into any one of these equations, and then I can get that y star equals to b over a plus b squared. And this is a unique fixed point, right? Because I only have x equals to b as I've shown here, and then the resulting y is a linear equation for that. So I know it's a unique fixed point. The next thing I do is I work out the Jacobian. Okay, so the Jacobian, you just take your derivatives. Here it is. It's basically minus 1 plus 2x squared y. The derivative with respect to y is a plus x squared, and minus 2xy minus a minus y squared. Okay, I evaluate the Jacobian at the fixed point. So I basically substitute x star equals to b and y star equals to that into this thing. And then I can work out the determinant, which is basically these two multiplied together minus those two. And it's actually a very nice, simple expression. It looks horrible when you're working it out, but it simplifies a lot. And I can get the trace. Okay, the trace is nasty. It's the sum of those two, and it looks like that. Okay, so now I've basically done my linear analysis. The only thing that's left is to find out what the nature of the fixed point is. Okay, and this is something you should, when you did the problem sets, I noticed that you should be a little bit more specific. So the first thing you do is you basically work out the determinant. Okay, so the determinant is greater than 0. That means it is not a saddle. Okay, then what you do is it's stable if tau is less than 0. In other words, if this beat is less than 0, and unstable if it's greater than 0. And then remember, then you must still distinguish whether it's a spiral or a node. So you must actually work out that square root. I'm just saying for future references when you actually answer those problems. But for this argument, I'm basically going to say it's stable if tau is equals to 0, it's unstable if tau is greater than 0, and it's a center if tau equals to 0, and that's the bifurcation point. It's the point at which it changes stability. Okay, so it's either a stable spiral or a stable fixed point here, and if it's greater than 0, it's an unstable spiral or an unstable fixed point, and this transition point is over here. And that's what we're interested in, because only if the fixed point it's going to turn out is unstable are we going to actually get glycolysis. Okay, so let's just work it out. If tau is 0, that's where the bifurcation takes place, this beast over here, which I've just multiplied out, is equals to 0. And I now want to know in which parameters we actually have this bifurcation point. In other words, when is our system going to change from a stable fixed point to an unstable fixed point? Okay, and I want to plot that because that's going to be important when I start actually looking to apply the Poincare-Bendixson theorem. Because if it's a stable fixed point, everything's going to go to the stable fixed point. If it's not a stable fixed point, that's usually when the limit cycle gets born. Okay, and we'll see this more clearly as time goes on. But for right now, I want to know, given this expression, when does my system change its nature? So I actually want to plot this expression in terms of A and B. Okay, and I'm doing it slowly because I actually want you to be able to do these things because they appear a lot. It's a generalization of our parametric or our implicit expression of a curve. So what's the first thing that I do? Okay, I run and hide. And after that, the first thing I do is I notice that this thing's quadratic in A. Okay, so I can actually write down an analytic expression for A. You could do that. What you could also notice, it's quadratic in B squared as well, and you know B is positive. So you can actually also write down an analytic expression for B squared. Okay. The next thing I do is I put a few points on the plot. Okay. Because so it's just guides that it's not this tremendous problem. So the first thing I notice is if A is equals to 0, then all I'm solving is b to the fourth minus b squared. Okay, so I'm going to put those points on. In other words, if a is equals to 0, b is equals to 0, I can have that point. That's a point on my curve. What's also true, if a is equals to 0, okay, and b is equals to 1, I have another point on the curve. Okay, so at least I know where two of the points occur. The next thing I'm going to do is, if I'm going to write down the full expression for a, right? So because it's a quadratic in a, I have a formula for a, just a quadratic formula, and I can write it down. And I then know, I look over here, this thing is always positive, it's the first thing I check, because b is positive. So there's no problem there. Okay, so for a given b, I can find a. The next thing I do is I work out where this thing changes. So in other words, when dA dB, which I can work out, is equals to 0, and it's equals to 0 if a equals to b equals to 0. Okay, and you can see that because b is on top here. So if b is equals to 0, it's equals to 0. If b is equals to 0, then we immediately have that a is equals to 0. So we know that dA dB is equals to 0 over there. So I put in this dotted line because that dA dB equals to 0 means that you have a tangent to your curve that is vertical. Okay, so I know when it's going to leave the origin, it's going to basically leave it like a parabola. Okay, and this is going to be the tangent to it. Because when dA dB is equals to 0, it's a turning point over there, and so you're going to be behaving it like, it's going to behave like a parabola. But there's another point where this thing is also equals to 0, it's over there, okay, and that you get by factoring out b and saying that minus 2, or basically 2 is equals to 1 over the square root of 8b squared minus 1, and then solving for b. Okay, so that second point over here is b equals to 3 over 8. You put it back into this expression over here, and you get what a is, and you put it in there. So you actually have your second turning point. You also put in this dotted line because you know it's tangent over there. And so what you now have, you have a function that goes through there. The only places at which it turns around is at this point and that point. So you basically have a function that's going to increase to here, be tangent to the vertical line over there, and then it's going to go back and decrease to the origin, and there you can draw it. Okay. And so the region in which you have an unstable fixed point is this region in red. Okay, so still just the linear analysis. We now know for which parameters the thing goes unstable, and we are interested in that because that's eventually going to be the thing that goes across the boundary into the bigger region and forms the limit cycle. Okay, that's basically everything you can learn from the linear analysis. So let's now try and plot the whole graph, or see what more we can say. Okay, so there's our glycolysis model. And we go through I won't say it's a recipe, but it's basically something you do every time. We plot the null lines. X dot equals to 0 occurs if you have this thing equals to 0. You try and write it as y equals to x over a plus x squared. And you also try and plot that. Okay, so you had a similar thing that you had to plot in the test. The first thing to note is you write down the asymptotes. Y goes to 0 as x goes to infinity. Okay, and as x goes to 0. Right? If x goes to 0, y is 0. If x goes to infinity, y goes to infinity. And so you have that fact. Okay. You know that in between there has to be a hump. Okay. So you work out the derivative, dy dx. You have that it's basically the denominator squared plus the numerator's derivative times the denominator minus the the numerator's derivative times the denominator minus the denominator's derivative times the numerator, and you simplify and you get that. And you know that that thing is equals to 0 when x is equals to the square root of a. When x is equals to the square root of a, you have y equals to 1 over 2 times the square root of a. Okay, so straightforward, but necessary to do in tests, necessary to do in problem sets. And so the next step is we're actually going to plot it. Okay, so we know the graph goes to 0 over here, it goes to 0 over there. In between, it has a hump at x equals to the square root of a. So we put in that point where it turns around, and so we know it increases from 0 to the turning point, and then it decreases from the turning point to infinity. So that's all you need to plot that guy. Okay, the next step you do is you choose points on the thing and you put in the arrows. You know the arrows are vertical because it's a null line, and you can see here it points down for large x. Then at some place over here it changes from pointing down to pointing up. Okay, and so you guess there's a fixed point there. If you were plotting the arrows by hand, I would pick one point on this side, work out that the arrow is up, pick one point on that side, work out that the arrow is down, and then wait until I've plotted the next null line. Okay, so let's now put in the fixed point. We derived the fixed point in the previous slide, and there it is. It's just below the turning point that we worked out over here, because b over a plus b squared is less than that. And here we have that it's over here at b as well. So there's our turning point. And now what we're going to do is we're going to put in the other null line. We know it's going to go through the turning point, and we want to see what happens. So here we have y dot equals to 0. So we have the graph of b over a plus x squared. We know that when x is 0, y is equals to b over a. Okay, so we put that point in. We know it's going to go through this point over here because the fixed point always lies on both null lines. And we know that if x goes to infinity, y goes to 0, but it goes to 0 faster than this other null line over here. Okay, so we draw the first null line, we know it's there, and it goes to a fixed point, and then we know as y goes to 0 as x goes to infinity, and the purple line has to lie below the teal line, and so we draw it in there. So that's our next null line. If you're unsure how far below, choose numbers, put them in, and actually plot the points in the graph. That's always the last resort, or often the first ones. I often put in a number of numbers and put points in to make sure I don't make a stupid mistake with my derivatives and stuff. Okay, put in the arrows. You know the arrows are horizontal, either left or right. You pick one point over here and you can put them in. You pick one point over there, you can put them in. Typically, if you have a normal type of fixed point, it's going to change direction as you cross the fixed point. Okay, now what you can see, what's going to happen, if you pick a random point over in this region, the arrows are going to point left and up, okay, because it's between the two null lines. If you pick a random point over here, it's going to go right and up. As you cross the null line over here, you go horizontal, so you're going to go right and down over here. So you can get a sense of what this problem is doing around the null lines. Okay, you can get the sense that this thing sort of wants to rotate. And you know that if this fixed point is unstable, then you have a spiral, it spirals out. So if you want to prove that you have a limit cycle, you need to find a box where everything is going across the box inward to prove that you have a trapping orbit. And that is something we now want to construct. Okay, so just more arrows. Now we want to construct the trapping region. And the first thing to note is we start constructing our box is that, and this is where the skill comes in. In other words, there's no recipe for constructing the box. You simply try and find lines that is going to contain this region. You can guess the action takes place around the fixed point, and you're going to try and find a box that's basically going to make sure that you can prove all the trajectories enter a particular region. So the first thing, a natural box is if y is equals to 0, in other words, the x-axis. If y is equals to 0, right, then y dot is equals to b, and we're given b is greater than 0. So if y is equals to 0 over here, y dot is always positive, so it's going to come up off the x-axis. So that's a very good line to choose. Okay, so there we have the one region of the box. So we know everything is flowing across this y equals to 0 line. The next place to choose is here on this other boundary over here. If x is equals to 0, x dot is equals to ay, okay? We know that y is positive and a is positive. This is greater than 0. So you've got this line that it basically increases across there. So we know at least that we have a valid boundary in the upper quadrant, the first quadrant, okay? So, but we need to have a bounded region, right? This is not enough because we need to show that the trajectories actually get trapped. And right now we've trapped our trajectories in the whole of the positive on the first quadrant. Okay, so now we want another thing. So the next thing to notice is so we're going to try and complete the box. If y is equals to b over a, so typically we want a thing over here, okay, and it needs to be above b over a, because anything below b over a, you're going to have these arrows crossing out of your box. Okay, so you do need to have it above b over a so that the arrows point downwards and go into the box, okay? So if you have y equals to b over a, then you know that y dot is less than 0, because both b and a are positive, and this is positive. So it goes down across this curve. Okay, so you can see how we're building our box up. And so we now have restricted this thing once again into an infinite domain, but it's only infinite in this direction. Okay, so everything, all our trajectories enter there. The next step is we want to draw another line that changes it, but we can't draw a vertical line because everywhere in this domain the arrows point outward like that. So a vertical line won't work. But we're not restricted to just a vertical line. We can have different kinds of lines as well. Like remember, we could have the polygon. And so the way we get what the next line is we look at what this thing looks like far away. Okay, so when x and y are much bigger than 1, okay, the only thing that dominates this equation is this final term. Okay, you have that x dot basically looks like x squared times y, and y dot equals to minus x squared times y. And so we basically, what you do to do this is you know that they sort of it looks like as if they're going to have a slope of minus 1, because you're going to have dy dx equals to minus 1. So then you say, let us examine what happens to the line, or a whole collection of lines, of y equals to minus x plus a constant. In other words, let's see if we can find a skew line with gradient minus 1 over here, such that everything goes across it. Okay, so we say, let's examine those lines, and we can work out what E dot is. In other words, what the potential, or what the trajectory does, what happens along a trajectory to this potential, and we can just work it out. So E dot equals to x dot plus y dot, and you substitute them in, okay, those two in there, and you simplify, and you get that it is equals to minus x plus b. So there you can see that E dot is negative provided x is greater than b. Okay, so you basically are going to need to choose E that crosses this line that you know is inward at x is equals to b, And when x, and it goes through this point b over a, okay, so what you then do is you substitute x equals to b and b over a into e, and you get that the special line that you want is when E star is equals to b over a plus b. Okay, so that's going to be the curve or the special line that you want that's going to ensure that the dot, E dot, is always inward across that line. Okay, and there you draw it. Okay, so for this line, you have proven that E dot is always positive. E dot is negative, it decreases across here. And therefore it's inward, and so you can see if you draw them very carefully, all the arrows are going to sort of go, they're going to still go skew, but they're going to all cross this line. So there you have an entirely valid trapping region, okay, because it's a finite region, it always goes inward across here, and you're done. Okay, so you now know that in that special region you're going to have that a trajectory always ends up there, and the thing that now remains is that you need to get rid of the fixed point, and the fixed point, if the fixed point is unstable, okay, then you're going to have the small circle around the fixed point where all the arrows goes out. So you can only apply the Poincare-Bendixson theorem if you can draw a little circle around the fixed point and you can prove that all the arrows are outward, and that's only possible if the fixed point is an unstable spiral or unstable node. Okay, so only in that red region that we did on the previous plot is the fixed point going to be unstable, and that's why the previous plot is actually important, because it actually tells you when your limit cycle exists. So if the fixed point is unstable, you put a little circle around it, you know it's always going to cross the little circle, and so now you have a trapping region that is in here. You can see that the trajectory always enters this region and it never goes to the fixed point. So what's going to happen is you're going to have a limit cycle that goes around the thing like that. And I'll show you in the next lecture, there's not going to be enough time now, what possibilities exist. In some sense, if you were to actually integrate this phase space or integrate these equations for different values of B, what the limit cycles are going to look like. But the only thing you know at the moment, or that you've proven, is that it's going to be in this region, and you say you've gotten a trapping region. They're definitely not going to be circular, but they are going to exist around that fixed point. Any questions at this point? No. That's basically all of the lecture for today. What I'm going to do during the tutorial